Hello everyone, welcome to the Introduction to Mechanical and Industrial Engineering course, MEC 130. In this video, I'm going to solve some examples as more practice on the different topics which are related to the fluid engineering. Over the previous video, we discussed the different subjects and topics related to the fluid mechanics, like what does it mean Newtonian fluid, the buoyancy force, the drag force, the pressure, in addition to some important application like the fluid flow in tubes. So in this video, I'm gonna solve these examples as more practice about the different equations and formula that we discussed over the previous video. So let us start with the first example, which is related to the shear stresses that would be acting over a Newtonian fluid. As we explained over the previous video, we defined the shear stress as tau equals the force divided by the area, which should be the shear force acting over the fluid system, and the area, this is the surface area of the fluid surface. In the meanwhile, it should equal to the viscosity times the average velocity or the velocity of the fluid at the tip divided by B, which stands for the thickness of the thin layer of the fluid. This is what we covered over the previous video regarding the definition of the Newtonian fluid and how we can calculate the shear stress acting over this Newton. So this example is a practice on how to use this expression for the calculation of the shear stress. And in this example, the slide of a machine. Many of the machines, for example, if we're going to talk about the RAM that it would be exist in the Shear machine, as we explained in the manufacturing part. In addition, for example, the carriage that would be exist in the lathe machine. So many of the machines, they depend on the slides. These slides, they should be used with lubricant. So the key idea of the lubricant is just to relieve or to eliminate the friction that would be exist between the slide and the other fixed surface. Like as shown here in the figure, this is like a slide. This thing, it should be moving right and left and over another another surface, which it should be stationary or fixed, not moving. So this one, to be freely moved over the surface, we are applying a very thin layer of oil that exists at the contact surface between the slide and the fixed base, kind of. So this is the slide, this is the thing that is going to slide, and this is the fixed part here. And there should be like a very thin layer of oil. This is gonna be if we're gonna consider this application from the fluid engineering point of view, this is gonna be very similar to the example that we explained over the previous video regarding the Newtonian fluid. Like we said that think that you do have one surface that is fixed, not moving, stationary, and the top surface is moving with a certain velocity and because of a certain force. And between these two surfaces, there should be some kind of fluid that is going to slide or to move or to be sheared. Actually, we said that there should be a shear stress, and the velocity of the fluid particle next to this surface should be 0, and the velocity of the particle that is already in contact with the top surface is going to take the same velocity. So we're going to end up with a distribution of the velocity between the two surfaces. This is known as the velocity profile, as we explained over the previous video regarding the Newtonian fluid. And this, in order to achieve or end up with this velocity profile, we have to apply a force, and this force will produce some kind of stress. This stress is known as the shear stress. This is the shear stress. And if you divided the force over the contact surface area, the surface area between between the contact between the fluid and the top surface or even the lower surface, you're gonna end up with the shear stress, which it should be in the meanwhile equal to the viscosity times the velocity of the top surface divided by B, where B stands for the thickness of this layer. This is what we explained over the previous video. So this is a typical example on using this expression. So we do have this slide of this machine that is lubricated by 8 centimeters times 40 centimeter oil layer. So this oil layer, which it should be this layer, had these dimensions. So these two dimensions, these are like the width and the length of this surface layer or this oil layer, and it should have a certain thickness, which we have no clue how much it is required to find the thickness of the lubricant oil film, how much it is. So the dimensions of this oil film it was given to us by 8 centimeter times 4 centimeter as dimensions, as in plane dimensions. It is better to convert the centimeter into meter, since all the other dimensions were given in meter, like the kilogram, like the viscosity was given as kilogram per meter second. The velocity of the top surface or the slide, it's gonna be 0.15 meter per second. So since everything is given in meter, converting a centimeter or millimeter into meter, so this is gonna make more simple in terms of the calculations. So to convert centimeter to meter, we have to divide by 100. So this is going to give us 0.08 meter times the 0.4, because you're going to divide by 100 meter. So I just did unit conversions. From these two dimensions, you can calculate the cross section, the area, the surface area of the film, of the oil film or the oil layer. Which when it is divided by the force, you're going to end up with the shear stress. When it is subjected, so it is required, or the slide of the machine is lubricated by 8 centimeter times 40 centimeter oil layer, when it is lubricated by 90 Newton force, so the amount of force that act over this layer, it is 90 Newton. This is the force that act over the slide. Think of it like this. This is the top layer, this is the slide, and this is the other fixed surface down there. So the force was already given to us by 90 Newton. Its sliding velocity was observed by 0.15 meter per second. So the sliding velocity, which is V into this expression, was given by 0.15 meter per second. So what should be the thickness of the lubricant oil film? What should be B? So B, it is unknown. In case that the viscosity was given to us by the viscosity, which is mu, was given by 1.5 kilogram per meter times second. We said that the viscosity, it is a measure of how easy this oil film could be flew between these two surfaces. So simply to calculate it, the first thing that we need to calculate the shear stress. Calculate the shear stress, which is tau, from the given force. So we would have the shear stress equal the force divided by the area. The force was given by 90, and the area should be the cross-sectional area of the thin oil film, or the contact surface between the slide and the oil film. As you can see, the dimensions were given as 0.08 cross the or times 0.4. So, but in this figure, we do have two areas, not just one area. So as you can see, the slide has two bases, like two parts, like two layers, side by side of oil that it located here. That it has the dimension of 40 centimeter length, and the width there is 8 centimeter. So if you multiply the 40 times 8 centimeter, this is gonna give us the area of one layer on one side. How about the other layer? We should multiply times 2 to end up with the total area, because here we don't have only one layer, we do have two layers. As you can see, this slide, it is sitting over the fixed surface over two layers, which are located side by side. Everyone has a surface area of 40 times 8. So we're gonna multiply times 2 to calculate or to consider the two layers. So the cross-sectional area in that case, it will be 40 times 8 times 2. But the 40 will be converted into 0.4 from centimeter to meter, and the 8 will be converted from centimeter to meter. It will be 0.08. So it will be 2 times 0.4 times 0.08. So it is important to observe why we did multiply times 2. Because we do have two layers which are located side by side. So this slide, it is lubricated by two layers, by two surfaces. So the area, it is not just 8 times 40, it will be the double of 8 times 40 area. If we did the calculation, we simply gonna end up with the shear stress 90 over this value. This is gonna give us 14066.24, and the unit, it should be Newton over meter square, which is equivalent to Pascal, because the force is still in Newton, and we converted all the area into meter, so we're gonna end up with meter square, because meter times meter gives meter square. So this is for the shear stress, and this is step 1. Then step 2, Your objective is just to calculate the thickness, calculate the requirement. Here it is required to find the thickness of the thickness B of this thin layer. So the shear stress that we got it here, it should equal to the force over area. We already got it. In the meanwhile, it is equal to the viscosity times the average or the velocity of the top layer of the slide divided by the thickness. And we are seeking the value for this thickness. So in that case, tau equals mu times V divided by B. So this should be nu or V, which stands for the velocity, divided by B, which is the thickness. We already got the viscosity as 1406.25 equal the viscosity which was given to us by 1.5 kilograms divided by meter squared. There is no need to convert this unit. This is the standard unit for the viscosity. This should be multiplied times the velocity which was given to us by 0.15 meter per second. 0.15 divided by the thickness, which we have no clue how much it is. So if you did some simplification and cross multiplication, we're going to end up with B. So simply we're going to say that B equals 1406.25. I'm sorry, it should be the other way around. It should be the multiplication of these two values, 1.5 times 0.15 divided by, because we're going to do like exchange between the numerator and denominator here. So this is going to give us 1.06.25. If we did the calculation, this is going to give us the thickness as 1.6 times 10 to the power negative 4 meter. Why it should be in meter? Because we have converted all the units into meter. How about if we are interested in finding this thickness but in terms of millimeter? To convert from meter to millimeter, multiply times 1000. This is to convert from meter to millimeter, as we knew. So this simply, if you did the multiplication, this is going to give us 0.16 millimeter. So this indicates that this oil film, it is very, very thin layer of oil that is enough. It is 0.16 millimeter. It is less than millimeter. So it is a very tiny, very small film that is located between the slide and the other surface that over which this slide is already moving. And this thickness of the film, it is sufficient enough. It is more than enough to give a good lubricant to the slide to freely move with an enough good velocity as 0.15 meter per second over this fixed surface. Make sense? So this is an example about as a practice on how we can calculate the shear stresses, how we can calculate the thickness, even we could calculate the velocity. In case that you already given the same example, but instead of giving you the velocity, you will be given the thickness, and in that case you will be required to calculate how much of the speed or the velocity of the slide over this surface. Or in other words, for example, if we already given the velocity and the thickness, what should be the viscosity of the oil that it should be used here, we can determine how much of this viscosity. Anyway, it is one single expression. Know how to understand the parameters. What does it mean if it is a force? What does it mean area is the area? Know how you can calculate the area. What does it mean the viscosity? What does it mean V? What does it mean B? Make sense? Another topic that we discussed in the previous video is the Beyonce Force. Or in general, we said that fluids are used in interaction with the solid objects. Like for example, like in this case, this fluid is already confined in a container. In the meanwhile, it is used to support another solid object that is floating over the water surface or the liquid surface. So all the time there should be some interaction between the fluid and solid objects. This interaction should be described in the form of a force. Some of these forces that would be generated between a fluid and solid object is the Buoyancy Force. In case that you have a solid object like this piece of fluid that is floating on the top surface of the fluid, so in that case there should be a Buoyancy Force, a push that comes from the fluid acting over this solid object, keeping on floating on the surface. In some other scenarios, in some other cases, we may have the entire solid object, it is immersed or submerged into the water, into the liquid. Still, there is a Buoyancy Force acting on it. So this is one of the things that we discussed, how we can calculate the Buoyancy Force. So the Buoyancy Force, we said that it equals the rho, which F stands for the fluid. So here we are talking about the density This is the mass density or the density of the fluid, times g, which is the gravitational acceleration, times the volume of the displaced fluid upon the addition or the submerging of this solid object into the liquid. According to the Archimedes principle, that is said that in case that you have a solid object that is submerged or immersed into the water or into a liquid, this solid object upon the addition of it or dropping it into the water is going to displace, is going to remove a certain amount of the liquid, or at least is going to give a rise into the level of the water because of these dropping the solid object into the liquid or into the water. This amount, if we collected the displaced fluid and we find the weight of this displaced fluid, we're gonna end up with the buoyancy force that is going to be generated from the fluid acting on the solid object. So this example, we are required to calculate how much is the buoyancy force that is going to be generated over this piece of food that is floating over the surface of this water. This buoyancy force is the thing that is needed to keep this piece of wood floating over the surface. Make sense? So how we can calculate it? This is the expression as we explained. It should equal, it depends on the density of the displaced water, the density of the displaced fluid, and the volume of the fluid that has been displaced upon dropping or floating this piece of water over the liquid. This piece of food over the liquid surface. Make sense? So to calculate this buoyancy force, I'm just gonna give you an approach. Like your objective is just to follow these steps. You can simply calculate this buoyancy force. But let us read the problem here. It is given that 2 centimeters times 2 centimeters times 4 centimeter wooden box. So this box, it is a cube of box that has dimensions 2 centimeters times 2 centimeters times 4 centimeters. So these are the dimension 2 centimeters times 2 centimeters times 4 centimeters. As I said, it is better to convert into meters. So this is going to give us 0.202 meter times 0.02 meter times 4. I'm sorry, it should be 0.04 meter. As I said, to convert from centimeter to meter, divide by 100. So these are the dimensions of this wooden box. We can simply do the multiplication of these 3 dimensions to end up with the volume of this wooden box, how much it is. That is floating on the surface of the fluid, of a fluid such that half of its volume, half of it is submerged into the fluid. This half, it is a critical thing. You should understand, as long as this object is floating on the surface. So we should know exactly how much as a portion, how much of the volume, how much of this piece of food is submerged already into the water. And the other part is already above the water. We do care about the part that is already submerged into the water, because this part, the volume of this part that is already submerged into the water, this part, this volume, if you calculate the volume of this part, is going to be equivalent to the volume of the fluid that you're going to substitute into this equation to calculate the buoyancy force. And this is the first step that you're going to calculate. You're just going to calculate the volume of the entire solid object. Then you're going to calculate the volume of the displaced fluid, and this volume of the displaced fluid, it should equal to the portion of the solid object that is submerged into the liquid or into the fluid. Then you're going to substitute into this expression. So the first step here, step 1, just calculate the volume of the solid object. So what should be the volume of this solid? It is like a cube. So it should be the multiplication of cuboid. It should equal to the multiplication of these 3 dimensions. So the volume of this solid. So S stands for the solid. It is 0.02 times 0.02 times 0.04. If we did the multiplication, this is going to give us at the end 16 times 10 to the power negative 6 meter cube. As we said, we are multiplying meter times meter times meter. This is going to give us meter cube. This is the volume of the solid object. This is the first step. Then the second step is just to find or calculate the volume of the displaced fluid. As we said, upon the addition of this solid piece of wood on the top of the liquid is going to displace a certain amount of the liquid. How much it is? This certain amount of the liquid, it should equal to the same volume of the portion that is already submerged into the liquid. So this, as already mentioned to us here, half of its volume, half of this piece of wood is already submerged into the water. How about if it is completely submerged into the water? So in that case, we're going to say that the volume of the displaced fluid will equal to the volume of the total volume of the solid. But in this case, we do have only half of it that is submerged. So the amount of the fluid that it will be displaced, it will have a volume that is going to be half the volume of the solid object. Why half? Because this fraction, this portion, this is what was given to us here in the given problem. Make sense? So it should be half. It means that it's going to be 8 times 10 to the power negative 6. It is already given by 16, so it should be half as 8 meter cube. And this is for the second step. So once we calculate the volume of the displaced fluid, we can simply plug it here or substitute into the Beyonce Force equation to find the Beyonce Force as required. So this is the last step. Step 3 is just to calculate the Beyonce Force. Which is FB. So as we said that the FB, this Beyonce Force, it should equal to the FB equals the mass density of the fluid times the gravitational acceleration times the volume of the displaced fluid. So the mass density of the fluid was given to us by, if the density of the fluid equals the 1,100 kilogram per meter cube, so that's why we converted into meter. The centimeter, to be consistent with the meter, we have to convert either the meter into centimeter or the centimeter into meter. So the easiest way just to convert the centimeter into meter, calculate the Beyonce force acting on this box or this piece of wood. So the density was given 1,100, and the gravitational acceleration, we said that we do have two values. For the gravitational acceleration, it is 9.81 in case that we are working with the metric system or international unit system, and this is what we are doing in this example. But in case that all the dimensions were given in inch or foot, and the force was given in pounds, so in that case we have to convert or use the 32.2 feet per second square for the gravitational acceleration. But here it is given, we are working with the metric system, so it should be 9.81 times the volume that we just calculated as 8 times 10 to the power negative 6. If we do the calculation, we're going to end up with something. Definitely it's going to be in Newton. As long as you are fixing all the dimensions in meters, any length, any dimensions in meter, and all the units for the density was given as kilogram per meter cube, and you're gonna plug or substitute for the gravitational acceleration as 9.81, you're gonna end up with Newton directly. So the Buoyancy force, if we did the calculations, this is gonna give us 0.0863 Newton. This is gonna be the Buoyancy force, and this is what was required in this example. Make sense? How about if the same example was given, but this object, it is not floating on the surface, somehow it is hanging in the middle into the water, into the liquid. It means that the entire volume, it is submerged into the water. So in that case, the only difference in the solution will be the second step. In the second step, we calculated the volume of the part of the displaced fluid, and we said that this is equivalent to the portion of the solid object that is already submerged into the water. In this example, it was half of it, so that's why we calculated half of the volume of the solid to end up with the volume of the displaced fluid. But in case that it is entirely or completely submerged into the water or the liquid, in that case the volume of the displaced fluid will equal to the volume of the solid object that you calculated in step 1. Make sense? Let us now consider another example that you have this piece of sphere, or like this is a solid object that has a spherical shape that is already hanging into the liquid, but we are holding this piece of solid object, this sphere, using a wire or using a cable. So this cable, it is a wire, and there should be a tension like a force. This is a tensile force that is going to be generated into this wire. If we try to cut the wire, this sphere will be dropped into the base of the container. It's going to fall into the bottom of the container or onto the bottom of this liquid. It means that to keep it hanging in the middle of the liquid, we have to pull it with this wire, with this cable. So it is required to calculate how much of tension that is going to be generated into this cable because of two things. Because of the weight of this spherical object, and we have to consider that there is a push, and the push that comes from the buoyancy force that comes from the fluid, it helps the cable on holding this object in the middle, because we have so many scenarios here. One of the things, for example, any solid object, it has a weight. And in case that the weight of the object it is equivalent to the buoyancy force that act, any weight for any object, it should be directed down. It is directed down. So this is the weight of this object. It goes down, it pulls down the object. But in the other side, there is a buoyancy force. And we said that according to the Archimedes principle, that this force, it should be all the time upward. It should be directed upward. So this is the buoyancy force. It works against the weight. So we have so many scenarios here. One scenario is that the buoyancy force, it is bigger than the weight of the object. If so, the object will be floating on the surface of the liquid, as in this case. So in this case, which one is bigger than the other one? The buoyancy force, it is bigger than the weight of the piece of wood. So this is one scenario, that the buoyancy force, it is bigger than the piece of wood. The buoyancy force is gonna keep on pushing. Even if you push, if you use your hand to immerse this piece of wood into the liquid and leave it, so it's gonna start to rise up till it will be completely floating over the surface. Because of what? Because of the buoyancy force. It is bigger than the weight of this solid object, so the buoyancy force is gonna keep pushing it till it will be floating on the surface. This is one scenario. The other option is that the weight of the object, it could be bigger than the buoyancy force. So if it is bigger than the buoyancy force, in that case, that the weight of the object, the weight, because of its weight, is gonna keep on digging, is gonna keep on sinking down into the liquid. It's gonna keep on going down into the liquid till it will hit to the base. Why? Because the weight, it is bigger than the buoyancy force. In some other cases, we may have the weight is equal to the buoyancy force, and in such a way that gonna keep the solid object hanging in the middle. It is not over the surface of the liquid. It is not at the bottom of the liquid or at the base of the container that contains this cup. Instead, it is just hanging in the middle. And in that case also, we still have the buoyancy force is equivalent to the weight. Make sense? So if we consider the scenario or the case that the weight is bigger than the buoyancy force, as I said, that this solid object, this sphere, is going to keep on digging down or moving down till it will be fixed or sitting on the base of the cup. But how about if we would like to keep it? It is heavy. Its weight, it is bigger than the buoyancy force, but we would like to keep it hanging in the middle. So in that case, we're going to use this wire to keep holding this sphere hanging in the middle, as already shown in the figure. So the question is, how much of tension that is going to be generated into this cable? This cable will be stretched. There should be a tensile force. How much of this tension force that is going to be generated in the cable, this is what is required in this problem. So a sphere with 8 millimeter diameter. As we said that any spherical object, it has only one geometrical parameter that can describe it, which is the diameter of this sphere. So the sphere has a diameter of 8 millimeters. So this is the diameter of the solid object, was given at 8 millimeter. We can convert it into radius if we are interested. So the radius of the sphere in that case, it will be 4 millimeter. As I said, it is better to convert millimeter or centimeter into meter. So this is gonna give us 0.004 meter. Divide by 1000. If you divide it by 1000, you're already converting it into meter. So this is the radius of this spherical object that is hanging in by a wire or a cable and immersed into the fluid. As already shown here, the entire volume of the sphere, it is already submerged or immersed into the fluid. But thanks to the wire, it is hanging in the middle. As shown in the figure, if the density of the fluid, so rho F, where F stands for the fluid, equals 800 kilogram per meter cube, while the density of the sphere, the solid object, was given, so rho S stands for the solid object or the sphere, it is 1,800 kilograms per meter cube. So he gave us two densities, one for the fluid, the other one for the solid object. Calculate the tension in the wire, how much it is. So how much is the tension force? Let us give it T stands for the tension. This is the tension in the cable. This is the tension in the wire, as it is required. To calculate it, something that you should understand, because we have so many different scenarios here. One option, one scenario, as we said, that the weight, it is bigger than the buoyancy force, so the tension, it should help the buoyancy force. While we are holding this or hanging this sphere with a cable or with a wire, the wire is gonna help the buoyancy force to overcome the descent because of the weight. The weight, it is bigger. So the tension force, it should be in the same direction, helping the buoyancy force. So it should be the tension, this should be the direction of the tension force. To calculate it, it should equal to the difference between the weight and the buoyancy force, as we're gonna calculate. So this tension, since it is the difference between the weight and the buoyancy force, we have to calculate the weight of the solid object first. We have to calculate the buoyancy force. And if we subtract it, if we consider the difference, this is going to give us the tension force, how much it is. Make sense? And this is what we're going to do. So the first step here, step one, is just solve the problem like you're going to calculate the buoyancy force, as what we have done in the previous example. Do the same. So the first step here was to calculate the volume of the solid object. So let us calculate the volume. Step one, calculate the volume of the solid object, which is Vs. So the volume of the solid object, it is, this solid object, it is spherical. It is a sphere. And the volume of any sphere that we knew from mathematics or geometry, it is 4/3 by r cube, where r stands for the radius of the sphere. 4/3 pi, this is just the expression, fixed in the expression for the volume of any spherical object in terms of its radius. So it should be 4/3 pi times the radius that we just calculated by 0.004 when it is converted to meter cube. So if we did the calculations, we're gonna end up with the volume as 2.68 times 10 to the power -7 meter cube. Why meter cube? Because we converted the volume already into meter. So this is the first step. It's just to calculate the volume of the solid object. Then the second step is to calculate the volume of the displaced fluid, which is the volume of the fluid or the displaced fluid. We said that it should equal to the portion of the solid object that is submerged already into the liquid. So we do have here the entire solid object completely, 100% is already submerged, 100% of the solid object is already submerged into the water. So what does it mean? It means that the volume of this fluid, that it will be displaced because of the submersion of submerging the solid object into the liquid, it should equal to the volume of the solid object itself. The whole volume of the solid object, not portion of it. So it will be the same volume as 2.68 times 10 to the power -7 meter cube. Once we calculate the volume, we can simply calculate the buoyancy force. How much is the buoyancy force? We said that the buoyancy force is equal to the density of the fluid times the gravitational acceleration times the volume of the displaced fluid. The fluid density was given to us by 800 kilograms over meter cube, so it is 800 times 9.81. Why? Because we are working with the metric system times the volume of the displaced fluid, which is 2.68 times 10 to the power negative 7 that we just calculated in step 2. If we did the calculations, we can simply calculate the buoyancy force in terms of Newton. Anyway, it is a force. We said that if you fix all the units as dimensions in meters and the density in kilogram per meter cube, you're going to end up with the volume of the fluid as, or the force, the buoyancy force, it will be in terms of Newton, which will be in that case 2.104 times 10 to the power negative 3. Make sense? Then the fourth step, so as you can see, these three steps are typically the same as we have done in the previous example. But here we need to calculate the buoyancy force, and also we need to calculate the weight of this solid object. The weight of any object is going to be almost the same expression as the buoyancy force. So now we're going to calculate the weight of the solid object that we just going to give it a symbol as W. So it stands for the weight. W stands for the weight. It should equal to the volume, the mass density of the solid object times G, but the volume of the solid object. As you can see, it is the same expression as the buoyancy force. This indicates that the buoyancy force, it is a weight already. It is the weight of the amount of the fluid that will be displaced because of the submerging of this solid object into the liquid. The same thing here, the weight of the solid is going to be the mass density of the solid times the gravitational acceleration, but times the volume of the solid object. So equals the density of the solid object, it is 1800 as given, times 9.81. We said that since we are working with metric system, it should be 9.81 times the volume of the solid object, which we calculated in step 1 by 2.68 times 10 to the power negative 7. If we did the calculation, this is going to give us 4.734 times 10 to the power negative 3. And again, it should be Newton the same way like the buoyancy force. Once we calculated the buoyancy force and the weight, we can simply calculate the tension. But as you can see, you should understand the scenario. Which scenario, which option that we have in that case. As you can see, the weight, it is bigger. If you're going to compare these two numbers, the weight, it is bigger than the buoyancy force. So what does it mean? It means that the weight is going to pull down the solid object, while the buoyancy force is going to push up the solid object, and there should be a tension that is needed to make it equivalent. But because the buoyancy force by itself is lower than the weight, it is smaller than the weight, it won't going to able to support and hold the solid object in the middle of the liquid. We need another help that comes from the tension. So as you can see, the direction of the tension, it should be the same direction of the buoyancy force. So in that case, and from the Newton's law of static equilibrium that we discussed before, that the sum of forces in one direction should equal to the sum of forces in the opposite direction. So what does it mean? It means that the tension and the buoyancy force, both are working against the weight. Both are of the same direction, but the weight is on the other side, in the other direction. So we already have the weight, we already have the buoyancy force. The only missing thing is the tension. So from this expression, we're going to say that the tension, it should equal to, if you just move the buoyancy force to the other side, this is going to give us the weight negative the buoyancy force. As I said, the tension is going to be the difference between the weight and the buoyancy force. So the weight we just calculated by 4.734 times 10 to the power negative 3, negative the buoyancy force, which is 2.104 times 10 to the power negative 3. If we do the calculations, we're going to end up with the tension in Newton. The tension anyway, it is a force. So doing the calculations, you're going to end up with the tension by 2.63 times 10 to the power negative 3 Newton. Make sense? So this is the amount of tension, as I said, that would be needed to help the buoyancy force holding this object hanging in the middle of the water, of the liquid, as already shown in the figure. Make sense? All right, so in this example, we do have a different scenario between the for the relation between the buoyancy force and the weight. For example, in this plastic board that has a diameter of 15 millimeters, so the diameter was given by 15 millimeter, which can be converted into radius as 7.5 millimeter. If you divide it by 1000, you are converting into 0.0075 meter. So we converted the radius into meter already. That would normally floating or float onto the water is attached to the bottom of a beaker or this container or this cup of water using a wire. So normally it should be floating on the surface of this liquid. So what does it mean? This indicates that the weight of this plastic ball, it is small in comparison to the buoyancy force. The buoyancy force, it is bigger. So if we try to put it inside the water, immerse it into the water, the pushing force or the buoyancy force is gonna push it up and it's gonna keep on floating on the surface. But thanks to this wire, the wire is gonna hold it to be hanging in the middle as already shown in the figure. So what does it mean this? We do have here a different scenario. Over the previous example, the weight was bigger than the buoyancy force and we used the wire to help the buoyancy force. The tension force was helping the buoyancy force against the weight. But now we do have the weight, it is smaller. It is lower than the buoyancy force. The buoyancy force is bigger than the weight. So it means that the tension in the cable or this wire is gonna help the weight. So this is the other scenario. This is the other option. Make sense? So if the density of the water or the liquid is already given, so this is the density of the fluid that is given by 1000 kilogram per meter cube, while the density of the plastic ball was given, the density of the plastic ball was given by 700 kilogram per meter cube. So as you can see that the weight, since the density of the solid object is smaller than the density of the fluid, this indicates that the weight of the solid object is more likely to be smaller than the buoyancy force. It is lower than the buoyancy force, and in that case, we should use this cable to help the weight. It means that the direction of the tension force, it should be the same direction of the weight. So this is the direction of the weight going down, and the buoyancy force, but unfortunately the buoyancy force is bigger, so the tension, the weight needs help with the aid of the tension. So the tension is going to be on the same side and the same direction of the weight. So what should be then the tension in the cable? The same typical example, so we're going to apply the same procedure. Step one is just to calculate the volume of the solid object, which it should be 4/3 pi r cube. It is a sphere. So it should be 4/3 the pi times the radius, which is 0.0075 cube. Do the calculations, you're going to end up with the volume as meter cube. Then the second step is just to calculate the volume of the displaced fluid. As you can see, the entire volume, the whole volume of the solid object is submerged into the water. It means that the volume of the displaced fluid should equal to the 100% of the solid volume, which should be the same solid volume, and then you can calculate it by meter cube. Then the third step is just to calculate the buoyancy force, which should equal to the density of the fluid times the gravitational acceleration times the volume of the fluid. So the volume of the solid object is 1.767 times 10 to the power negative 6, and definitely it's going to be the same volume, 7 times 10 to the power negative 6. Then the mass density of the fluid was given to us by 1000, so it should be 1000 times 9.81 times the volume, which is 1.767 times 10 to the power negative 6. If we do the calculation, this is going to give us the times 1000, it will be 0.0173. And what should be the unit? It should be Newton. Anyway, the buoyancy force, it is a force, so it should be Newton. Then the fourth step is just to calculate the weight of the solid object, which should equal to the mass density of the solid object times the gravitational acceleration times the volume of the solid object, equals the density of the solid object, it is given to us by 7,000 kilogram per meter cube. So it should be 700, I'm sorry. So it is 700 times the gravitational acceleration 9.81 times the volume of the solid object, which is 1.767 times 10 to the power negative 6. If we do the calculations, this is going to give us the 0.1012135 Newton. So we got the weight, we got the buoyancy force. As you can see, the buoyancy force, it is bigger. It is here 0.017, but here it is 0.012. It means that the buoyancy force, it is bigger than the weight. So we need the tension to help the weight to keep holding this plastic ball in the middle or hanging into the liquid or the water. Make sense? So the last final step then, it will be that the tension, it should equal to, as we said, that the tension and the weight both should be over the same side. So the tension and the weight should be on the same side, but the buoyancy force, it should be on the other side. The tension and weight, they are helping. It means that the tension helps the weight. So we're gonna end up that the tension, it should equal to, just move the weight to the other side. The tension will be the buoyancy force negative the weight. So it will be the 0.01734 negative the 0.012135. If you do the calculations, just find the difference. This is going to give us the value of the tension. Negative 0.7. So it will be 5.2 times 10 to the power negative 3 Newton. This is going to give us the tension force, how much it is that is needed to keep this plastic ball hanging into the water. Make sense? Alright, so one another example that includes a very important application of the fluid engineering, which is the calculation of the pressure at different levels deep into the water or into the liquid. Like for example, if you do have a liquid, and let us assume like 3 levels of the liquid that already this is the top surface, so we're gonna say that this is like level 0. So assume that this is level 0, and assume there is another level 1 and another level as 2. And let us assume that the height between level 1 and 2 is or 0 and 1. Let us give it a name like the height between 0 1, and we do have another height between the two levels as h1 and 2. So simply, if there is a solid object like human being who is already diving into the water or swimming deep into the water at level 1 or level 2, so you're gonna feel with some pressure, as we mentioned before, that acting over this guy. So in this example, it is required to calculate the difference in the pressure acting on two objects immersed into the water. So assume that we have two objects. One object is already located at level 1, and there is another object that is located at level 2, deep into the water. So this is the surface, the sea surface, or the liquid surface, or the water surface, and we do have two objects that already immersed into the water at two different levels. So there should be a pressure that is going to generate due to the weight of the column of the water above the object 1, and there should be another pressure or acting over the second object due to the weight of the column of the water that is already above the second object. So as we go deep into the water, the pressure is going to increase. So the question is, what is the relation between the pressure that acts over the object 1 and the pressure that acts over object 2? We can even have a pressure here as B0, the pressure at level 0. So these are the pressures at these 3 different levels that we define here. So if we are interested in calculating the pressure at level 2, we have to refer to another pressure at any other level. Like for example, I can calculate the pressure of level 2 at level 2 with respect to the pressure at level 0, or with respect to the pressure at level 1. It depends. So here we can express or write the pressure or calculate the pressure in 2 different ways. I can refer to the pressure at level 1 in case that you already have an idea about the pressure at level 1, how much it is, plus the rho of the fluid, the density of the fluid, times g, the gravitational acceleration, times the height between the 2 levels. the height between level 1 and level 2. Also, I can define the pressure at level 2, but with respect to the pressure at level 0, in case that you do have an idea about the pressure at level 0, plus the density of the fluid times the g, which is the gravitational acceleration, times the height between the two levels, level 0 and level 2. The same thing, if we are interested in calculating the pressure at level 1, you can refer to either pressure 2 or pressure 0. It's up to you. Either option, but mainly this depends on the given information, on the given data. Also, something else that you should understand, that the pressure at level 0, which level 0 typically is going to be the surface, at the top surface of the liquid. In many of the cases, this pressure is going to be equal to the atmospheric pressure. This atmospheric pressure, which comes from the column of the air above the sea surface or the surface of this liquid water. In many of the cases, if you're going to compare the atmospheric pressure to any other pressure underneath the sea surface or the liquid surface, like pressure 1 or pressure 2, the atmospheric pressure is very negligible. It is very small in comparison to P1 or P2. So in that case, we can neglect the atmospheric pressure, as he already mentioned here, neglect the atmospheric pressure if we are interested to refer to the B0. It means that you're just going to assume that B0 equals 0 in that case. Why? Despite it should be equal to the atmospheric pressure, but in this case, we are neglecting the atmospheric pressure. It means that the pressure at level 0 is already 0. Make sense? So in this problem, it is required to calculate the difference in the pressure acting on two different objects immersed into the water. The first object is 2 meters deep in the water. The first object, which is this one, is 2 meters deep. It means that this height, it is 2 meters deep into the water, while the other object or the second object is 5 meters deep into the water. It means that this total height, it is 5 meters. So what should be the distance between the two objects, 1 and 2? It should be 3 meters, which is the difference. So this total distance, it is 5. This is just 2, so the difference is going to give us 3 meters. Make sense? So it is required to calculate the pressure difference. What does it mean, pressure difference or difference in the pressure? It means that the difference between the pressure that acts over the object 2 negative the pressure or the difference between the pressure P2 and P1. Because these are the two objects. One is located at 2 meters deep. The second one 5 meters deep in the water. So the difference between the two pressures, this is going to give us B2 negative B1, which it should be the difference. Delta B stands for the difference of the pressure. So simply I have to use this expression. If I use this one directly, simply if you move P1 to the left side, just move P1 to the left side, you're going to end up with B2 negative B1. It should equal to, from this expression, as rho F G H between the two levels 1 and 2. And H, the height between the two levels, we already got it by 3 meters from the geometry and the dimension that already given to us. And the water density, the density of the fluid was given by 1,000 kilogram per meter cube. G is well known as the gravitational acceleration, so we can calculate the pressure difference between the two levels 1 and 2 equal the density, which is 1,000 times the 9.81. We said that since we are working in the metric system, we have to define the gravitational acceleration by 9.81 times the height between the two levels, which is already 3 meters. If we do the calculation, we're going to end up with the pressure, which it should be in Pascal. The pressure automatically should be in Pascal, which is equivalent to Newton over meter square. So do the multiplication, 1,000 times 9.81 times 3. This is going to give us 2,000 or 29,430 Pascal. So it means that the difference in the pressures at level 1 and level 2 is going to be this value. If we know the value of the pressure at level 1, we can simply calculate the pressure at level 2. Or if we know the pressure at level 2, we can determine the pressure at level 1 using these expressions. Make sense? So this is one of the important applications, is to know how we can calculate the pressures at different levels deep in the liquid. One another important application here is the fluid flow in pipes or tube, like water flows in a tube. So for example, if you have a fluid and this is the tube, and there should be some fluid that already flows inside the tube. We said that we're going to end up with a velocity profile, that the speed or the velocity of the fluid will be zero at these contact surfaces or at the internal surface of the pipe or the tube, and then it's going to increase to be maximum. This velocity, it will be maximum at the center of the pipe or the tube, and then it will be descending or decreasing one more time to be zero again over the other side. So this is going to give us the velocity distribution or velocity profile of the fluid flow inside the pipe or the tube. And we can describe the equation, or the equation that can describe the velocity variation or distribution over the radial direction. We said that this is like the center line of the pipe, and this is going to be R, which identify the location, the radial position of any layer that belong to this fluid inside the tube. We can determine the velocity at any location, at any layer, using this expression, where R uppercase, this stands for the inner radius. This is the inner radius of the tube. While the V maximum, this is the maximum velocity that can be calculated as the D square, where D, this is the double R. D, this the diameter, it is the double the radius. This is the diameter of the pipe or the tube. Delta B, which is the pressure difference between the two ends of the tube. We said that one side it should be with a bigger pressure to push the liquid to flow in a certain direction, and mu, this stands for the viscosity, and L, this stands for the length of the pipe or the tube. So this is the L. Make sense? Once you calculate V maximum, you can plug it here. You're gonna calculate the velocity at any position R depending on R. So the R is the thing that it varies, that it changes as we explained, and once you calculate, as I mentioned, the V maximum, you're going to substitute it here. You're going to end up with the velocity at this R. If we are interested in the average velocity, we said that in some application, we would be needed to calculate the average velocity. It should equal to the half, the V maximum, the maximum velocity for this application. And this is the volume flow rate that indicates how much of volume that is going to flow over certain section through a certain section per unit time. This is going to be one of the important parameters that we would need it for some certain application. So this example, it is a practice on how you can calculate all of these different physical quantities or these quantities for this type of application of fluid flow in pipe. So a fluid with a velocity of 4 kilogram of a viscosity, of 4 kilogram per meter second. So the viscosity, which is mu, was given by 4 kilograms times divided by meter second. And the density, so this is the density, rho of the fluid, was given by 800 kilograms per meter cube. Is subjected to a pressure drop. So the pressure drop, this is delta B. This delta B, this is the pressure drop, which is already given to us by 100 kilopascal. So make sure that you unify the units. Once you extract this given data, unify the units. So kilogram is good, it is fine. Meter per second, this is the standard unit, the basic unit for the viscosity according to the metric system. This is the density, the basic unit of the density according to the metric system. But here we do have kilopascal. We have to get rid of the kilo. So this is gonna give us 100 times 10 to the power 3 to get rid of the kilo, the pascal. Makes sense? So I just did conversion here. To flow in a pipe with 80 millimeter diameter. So the diameter of the pipe, it is 80 millimeter. We can convert it into meter by dividing this value by 1000. So this is going to give us 0.08 meter. Directly, we can calculate the radius. It should equal to the 0.08 divided by 2, because the radius, it should have the diameter equal to the half the diameter. So it will be 0.04 meter. And 2 meter length. So the viscosity was 4. The density is given by 800. The pressure drop, which is delta B, it is 100 kilopascal. We converted it to Pascal to flow in a pipe with 80 millimeter diameter. So the diameter had been converted into meter, and the length was already 2 meters. So there is no need for unit conversion for the length of the pipe. It is already given by 2 meters. And it is required, assuming a laminar flow. We said that we do have a turbulent flow and laminar flow, and we said that all of these equations are only acceptable as long as we are working as laminar flow. For a turbulent flow, the things or the equations, these equations are not valid. We have to use different techniques and different things, which is more complicated, and anyway you're going to study this in the fluid mechanics course. So it is required, if we assume that laminar flow, that we have a laminar flow, it means that we can use this equation, calculate these requirements. So the first thing, what is the maximum velocity of the fluid in meter per second? So the maximum velocity, which is this expression, so simply, this is A, requirement A, the V maximum equals, according to this expression, it should be the diameter squared, delta B, the pressure drop, divided by 16, mu, which is the viscosity, L, this is the pipe length. So the diameter is given by 0.8 squared times the pressure drop, which is 100 times 10 to the power 3 to convert to Pascal, divided by the 16, the viscosity was given by 4, times the length of the pipe, which is already given to us by 2 meter. So it is 2 meter. Do the calculations, you're going to end up with V maximum. So 0.8 squared times 100 times 10 to the power 3 divided by the 16 divided by 4 divided by 2, this is going to give us 5. So it will be 5. What should be the unit? Meter per second. And this is the unit that you have to find the velocity with, which it should be in meter per second as required here. So if you make sure that all the units, all the dimensions are in meter, in Newton, in kilograms, the basic units of the metric system, definitely you're going to end up with the velocity in terms of meter per second. This is for requirement A. For requirement B, it is required to determine the fluid's average velocity in meter per second. So the average velocity intuitively is going to be half the V maximum that you just calculated. So V average, it should equal to half the V maximum, which we just calculated. So this is going to give us 5 over 2, which it should be 2.5 meter per second. This is for the second, for buoyant B. For buoyant C, it is required to calculate the volume flow rate. So this is the expression for the volume flow rate, which is Q. Q, it is pi d bar 4 delta P divided by 128 mu L. So it's going to be the pi d bar 4. I'm sorry, this is the Q. So the Q, it will equal pi d bar 4 delta P divided by 128 mu L. Then your objective is just to direct substitute. So the diameter is already given by 0.08. So it is 0.08 square, bar 4 times pi. Don't forget the pi. Delta B, which is already given as 100 times 10 to the power 3. Divided by 128 times the viscosity, which is 4, the length, which is already given by 2 meter. So do the calculations, we're going to end up power 4 times pi times the 100 or 10 to the power 5 divided by 128 divided by 8. So this is going to give us 0.01256. What should be the unit? Meter cube per second. This is the unit for the volume flow rate. It should be volume per unit time. So it should be volume as meter cube per unit time, which is second. So it will be meter cube divided by second. This is going to give us the volume flow rate. And this is for buoyant C. For buoyant D, calculate the Reynolds number. We said that Reynolds number, it should be less than 2000 in order to indicate a laminar flow. In case that the Reynolds number it is bigger than 2000, it means that we're gonna have a turbulent flow. So it is required to calculate the Reynolds number. This expression was not given in the slides, but it is already given to you here in this problem. So your objective is just to direct substitute with the given information. So if we decided to calculate this Reynolds number, so RE stands for Reynolds number equals the rho F, which stands for the density of the fluid. So this is the mass density of the fluid, times the V average, the average velocity, times the D, the diameter of the pipe, divided by mu. Something that you should understand, that this Reynolds number, this expression of the Reynolds number only for pipes that flew inside the tube and in case that would have a laminar flow. But in general, for any other application, this expression for the Reynolds number will be different from one application to another application. For example, if the fluid flows in a slit, like between two layers, the Reynolds number expression will be different. So this is just only for fluid that flows in pipe. So anyway, the fluid density was given to us by 800. This is the fluid density, so it is 800 times the average velocity that we just calculated by 2.5 times the diameter, which is 0.08, divided by the viscosity, which is 4. If we do the calculation, you're going to end up with a number, and this is just a number. It has no unit, so it will be 800 times 2.5 times the 0.8 divided by 4. This is going to give us 40. As you can see, the 40, this is the value of the Reynolds number. It is less than the 40, the Reynolds number, equals 40, which is less than 2000, which indicate a laminar flow, as already given to us. It means that all the equations that we use for this problem were valid. One more example which is related to the same application, which is fluid flow in pipes or tubes. In an experiment, a thing that we have done, or we are performing an experiment, and it was required to calculate the viscosity of the fluid. Like we are performing an experiment to determine the viscosity of a specific fluid, which we have no clue how much is its viscosity. So the fluid was pressured to flow in a pipe with 20 millimeter diameter. That we arranged a pipe. Think that we do have a pipe. This pipe has a diameter of 20 millimeter. So the 20 millimeter, this is the diameter, it is 20 millimeter, divide by 1000, you're gonna convert it into 0.02 meter. And it has a length, so the length of the pipe, it is 500 millimeter. So if you divide it by 1000, this is gonna give us 0.5 meter. It is half a meter. When a pressure drop of 50 kilopascal, it means that the pressure difference between the two ends of the pipe, this delta P, was given by 50 kilopascal. We said that to get rid of the kilo, you're gonna multiply times 10 to the power 3 to convert it into pascal. Was applied, the fluid's average velocity was observed by 0.25 meter per second. So the average velocity, we said that we have multiple velocities, different velocity. We have a velocity at every layer that can be calculated using this expression. We have a maximum velocity, we have the average velocity. So we measured the average velocity of the fluid during the experiment, and we got it by this value as 0.25 meter per second. So the question is, find the viscosity. How much is the viscosity of the fluid? So we're gonna use the same expression. So as you can see, your objective is just to find this V average. Do the calculation like you just calculated follow the procedure just to calculate the V average. To calculate the average velocity, what you would be required to calculate first, you are required to calculate the V maximum. Once you find the V maximum, multiply times half, you're gonna end up with the V average. Just proceed like you are solving this problem for finding the average velocity. Make sense? So simply what you're gonna do, just substitute for the V average, which should be half V maximum, and substitute for V maximum as d squared delta P divided by 16 mu L. So simply, we're gonna say that the V average, since the V average, it is half V maximum, and we already have half the V maximum, we already have it by d squared delta B divided by 16 mu L. Then your objective is just to substitute with everything. So you're gonna end up with one equation that has only one unknown, which is the viscosity, and that's it. So it is a very direct substitution problem, straightforward problem. So the V average, it is already 0.25, it was already given to us, equals half times the diameter of the pipe, which we just converted into meter as 0.02 square, times the pressure, which is 50, times 10 to the power 3, divided by the 16 mu. We have no clue how much it is unknown, but the length of the pipe is 0.5. So you're gonna end up with the equation with only one unknown, which is the viscosity. So your objective is just to do the math do the calculations to calculate and cross multiplication, you're gonna end up with the viscosity, how much it is. So if you did the math, you're gonna end up with the viscosity with this value. So it will be like, you just gonna multiply, let me simplify, do some further step of simplification to make it easy for you. So if you multiply the 2 times quarter, so this is gonna give us 0.5 equals. Then do the calculation for all the number except the mu. So just keep the mu in the denominator and do the other calculation. 0.2 square times 50 times 10 to the power 3 divided by the 16 divided by the 0.5. So this is gonna give us on the top here 2.5. Then cross multiplication, you're gonna end up with the viscosity will be 2.5 divided by 0.5. This is gonna give us at the end 5. And the unit of the viscosity, it should be kilogram per meter second, as we mentioned before. So this is gonna give us the viscosity of the fluid that we got through this experiment. Make sense? You would be given the exact same example, for example, in this case, we, instead of calculating or measuring the fluid's average velocity, we could calculate the maximum velocity of the fluid. So in case that this value is the maximum velocity that we measured, there is no big deal. We're gonna still have the same procedure. Your objective is just to get rid of this half, but you're just gonna apply the same procedure and you're gonna end up with a different value for the viscosity. Another option is, instead of measuring the average velocity of the fluid or its maximum velocity, we could measure the volume flow rate. And this is one of the easiest approaches and experiments that we can simply measure. Experimentally, we can determine the volume flow rate. It is much more easy to determine it when compared to the measurements of the fluid velocity, whatever maximum or average velocity. So the volume flow rate, it is an easy approach to determine. So in case that the volume flow rate was given to you, so instead of using this one of these equations, you're gonna use this equation to determine the viscosity. You still have the same approach, one equation with one unknown, that can be simply solved to determine the viscosity. Make sense? Alright, so one last example here is this, which is related to another important application or one type of the important forces that would be generated in case that would have a solid object that moves with a certain velocity through an stationary fluid. Like, for example, you drive it, as we mentioned over the previous video, like when you drive your car over the highway, so there should be some kind of drag. There should be some kind of resistance that is going to act because of the stationary weight over the surrounding, over the highway. And as you speed up more, the drag or this resistance will be increasing. So this is known as the drag force that can be calculated using this simple equation, which is 1/2 rho, which is the density of the fluid, times the A, which is the frontal area. This is like projected area that depend on the geometry and the shape. And I showed you a table that determined this frontal area, how it would be changing from the application, from one between cars and bicycles, between sedan cars or trucks and so on. Also, this is the average velocity by which this object, solid object, is already moving through the stationary fluid. And CD, this stands as the drag coefficient. And this drag or coefficient of drag, it is different, as I mentioned, from one application to another application. In addition to the drag force, there is a power. So the power is the drag force times the velocity, the average velocity of the object. And this power, this is the minimum power that the object needs in order to be able to resist or overcome or push against the resistance that comes through the stationary fluid. Like while you're driving the car, this is the minimum power that your car should have in order to be driven, in order to be traveling over the highway. If the power that is delivered from the engine of your vehicle, it is less than this power, the car won't gonna be able to move. The car will be stuck in the middle, that is stuck against the air that is already facing the car or resisting the car. You could probably don't feel that this resistance, but think of it if you try to drive the car in the sea. It won't gonna go through the fluid easily because it is more dense fluid, it has more density, so the resistance is bigger. So this requires a very high thrust power and energy to push against this stationary fluid, so it could be moved against the drag force. So in this example, it is required to calculate the power. This power, which we can calculate it, we can determine the power. We can write the power directly by substituting Fd as 1/2 times rho, which is the density of the fluid times the frontal area. V, it will be V cubed because you're gonna multiply one more V here, so it will be cubed. CD, which is the drag coefficient. So how much of power needed by an automobile with a frontal area? So the frontal area, which is A, is already given as 2 meter square. Make sure that it is in terms of meter. So what should be the power needed by an automobile that with a frontal area of 2 meter square to drive or to travel at a speed of 120 kilometer? It should be kilometer per hour. It should be kilometer per hour, not kilograms per hour. The air density, so the average velocity by which the speed of this car, it is V average, which is this V, equals 120 kilometer per hour. So we have to convert it to the basic unit of the velocity, which it should be only meter, but per second. So first of all, we have to get rid of the kilo, which it should be on the top. So it should be 120 times. Then we're gonna do unit conversion for the kilometer into meter. So we're gonna multiply on the numerator by times 10 to the power 3 to get rid of the kilo. And in the denominator, we're gonna convert the hour into seconds. So we're gonna multiply times 60 times 60. So this is gonna give us 3,600 in the denominator. If we do the calculation, this is gonna give us 33.34 meter per second as a speed. So the speed of the car in terms of meter per second, we have to convert it to meter per second. This is the basic unit for the velocity. Then we can directly calculate the power, but we need the density of the fluid, which is 1.2 kilograms per meter cube, is already given here. The air density 1.2 kilogram per meter cube, and the coefficient of drag, which was given, which is CD, is given by 0.3. So simply the power then, we can calculate it, the power. It will be directly equal 1/2 the density of the fluid times the frontal area V cube, the CD, which is the coefficient of drag. So it will be 1/2 the density, which is 1.2 times the frontal area, which is already given by 2 meters square, times the average velocity is 33.34 cube, times the 0.3, which is the coefficient of drag. Do the calculations, you're going to end up directly with the power in terms of watt, which is equivalent to joule over second. This is the basic unit for the power according to the metric system. So if we do the calculation, this is going to give us 33.34 to the power 3 times 0.3 to 1.2 times half. So this is going to give us 13,034 1.33 watts. So this is the total power. This is the minimum power, as I said, that this automobile needs in order to overcome the drag that comes from the air as air resistance. And it means that the car should provide, or the engine of the car should provide or give to the car a power which it should be bigger than this value, so in such a way that the car would be able to travel at this speed. If you're gonna speed up more, it means that more power and more energy will be needed in that case. Make sense? So that's it. The objective of this video is just to give you some examples and some practice on these different applications that we considered over the previous video regarding the fluid engineering. Make sense? So that's it for today, and thank you so much for watching, and see you in another video.